There are infinitely many prime numbers. Proof by contradiction. If we plot prime numbers on the number line, we see that they thin out as they become increasingly large. And on the diagram at the top of the page, we see that the gaps between the prime numbers increase in size as the prime numbers increase in size. So down here, where the prime numbers are small, the gaps tend to be small. And up here, where the prime numbers are large, the gaps tend to be large. And given that we can see that the prime numbers thin out, we can validly ask the question, do they become so sparse that we eventually reach the final prime number? And the answer to that question is no, because in fact we can prove that the set of prime numbers is infinitely large. This fact can be proven in many different ways, but in this video I'm going to show a proof by contradiction. And I ought to point out that although many people refer to this as Euclid's proof by contradiction, in fact it is not due to Euclid. Euclid proved this fact using a different method. Let's first review the idea of proof by contradiction by way of an example. I shall prove by contradiction that the square root of 101 is less than or equal to 10.1, and we shall call this inequality statement P. First, we assume that P is false, i.e. we assume that the square root of 101 is greater than 10.1. I shall call this new inequality statement Q. Now we derive a false statement from statement Q via a mathematical argument, and that is straightforward. First, if the square root of 101 is greater than 10.1, then by squaring both sides, 101 is greater than 10.1 squared. But 10.1 squared is 10.1 times 10 plus 0.1, and multiplying that out via crab clause, we get 101 plus 1.01, which is clearly greater than 101 because 1.01 is a positive number. And so that tells us that 10.1 squared is greater than 101. And if we combine that fact with the inequality 101 is greater than 10.1 squared, we see that we have shown that if the square root of 101 is greater than 10.1, then 101 is greater than 101. And this statement, 101 is greater than 101, is false. Now, since we have derived from Q a false statement, we conclude that Q is false, which means that P is true. And of course, P was the statement that we wished to prove. Now, this method of argument relies on the following fact from mathematical logic. If you ever have an argument that starts with a statement Q and derives from it a false result, then Q is false. Or to put it another way, if your argument ends up with a false statement, then you must have started with a false statement. Or to put it yet another way, you cannot produce a false result from a true statement, as long as the reasoning in your argument is correct, of course. Our proof that the primes are infinite relies on the Fundamental Theorem of Arithmetic, which is a result with which you are already familiar. It says that every integer n greater than 1 is either prime, for example, if n equals 17, or it can be written in only one way as the product of prime numbers. So, for example, if n equals 24, we can write it as 2 times 2 times 2 times 3, or as 2 cubed times 3, where 2 and 3 are prime numbers. And usually we decompose a number into its prime factors, as they are called, using a factor tree, like so. And so we have the following theorem: there are infinitely many prime numbers. Or to put it another way, the set P is infinitely large. And the proof is by contradiction. First, we assume the opposite of what we are trying to prove. So we assume that the set P is not infinitely large, which means that it must be finite. And we say that there are exactly k prime numbers. So we could write our set P by assumption as P sub 1, P sub 2, P sub 3, up to P sub k, where all of the P sub 1, P sub 2, P sub 3, etc. are prime numbers. And note that that means that all of the P sub 1, P sub 2, and so on are greater than or equal to 2. Of course, here k is just some arbitrary integer. It could be 1, 100, 1 million, it doesn't matter. Firstly, we make a new number, q, which we do by forming the product of all the prime numbers in our set P. So we multiply together P sub 1 up to P sub k, and then we add 1. And we note that q must be an integer, which means that we can apply the fundamental theorem of arithmetic to it. Now, recall that all of the P sub 1 to P sub k numbers are greater than or equal to 2, and from that fact, it should be obvious that q is larger than P sub 1, larger than P sub 2, and indeed larger than all of the numbers in our set P. In addition, q must be greater than 1. Now, although I said it's obvious that q is larger than the P sub 1 up to P sub k numbers, we can in fact prove this if we have to, using the rules of inequalities. I won't do so in this video, however. Now, since q is larger than any of the numbers in the set P, it is clear that q is not equal to any of the numbers in that set, and hence q cannot be a member of the set P. Now, since we assumed that P is a finite set containing all of the prime numbers, this implies that q is not a prime number. But q is an integer, and q is larger than 1, so we can apply the fundamental theorem of arithmetic to it. And that tells us that q is either itself prime, or can be written as the product of prime numbers. Now, suppose that q is indeed prime, i.e. that we test it and it turns out that it only has 1 and itself as factors. So this is A. In this case, then, q is a prime number. We know that because we tested it. But q is not a prime number by assumption because we know that it differs from each prime in our original list, which we assumed to be complete. And so in this case A, we have that q is both prime by testing and not prime because it is not a member of the set which we are assuming contains all of the primes. And so we have produced a contradiction, which is a false statement. So from our original assumption, which was that there are finitely many prime numbers, we have generated a false statement, a contradiction, and so our original assumption in case A is false, i.e. there cannot be finitely many prime numbers. Now we consider case B, which is where q is composite, i.e. not prime. Then, by the fundamental theorem of arithmetic, it can be written as the product of primes. I.e., we can find some prime numbers, which I will call r sub 1 up to r sub n, in our set P, such that when we multiply them together, we produce q. Now, let's consider specifically the prime number r sub 1. We can now show that none of the numbers in our set P, i.e. none of the numbers P sub 1 up to P sub k, can be equal to R sub 1. And we prove this by contradiction. So we want to show that each of the P sub 1 to P sub k differ from R sub 1. And we do so using a proof by contradiction that is contained in this red box. We first assume the opposite of what we wish to prove, and here we assume that r sub 1 equals p sub 1, though please note that the same argument will work for p sub 2, p sub 3, and so on. So there is nothing special about p sub 1. Now, by the fundamental theorem of arithmetic, Q can be written as r sub 1 times r sub 2 all the way up to times r sub n. So Q divided by r sub 1 becomes r sub 2 times r sub 3 up to times r sub n, because we can cancel the r sub 1 on the top and bottom of the fraction. And that is obviously an integer, because r sub 2 up to r sub n are all integers. But note also that since we are assuming that r sub 1 equals p sub 1, then q divided by r sub 1 equals q divided by p sub 1. And we know that we formed Q as p sub 1 times p sub 2 all the way up to times p sub k plus 1. And we divide that by p sub 1 to give us p sub 2 times p sub 3 all the way up to times p sub k plus 1 over p sub 1 by dividing out the sum on the top of the fraction. But note that since p sub 1 is greater than or equal to 2, since it is prime, then 1 over p sub 1 must be less than or equal to a half, but also greater than 0. And so this quantity in the blue box cannot be an integer, since we are adding an integer and a fraction, 1 over p sub 1, which is less than or equal to a half. And now we have a contradiction, since we have shown that if r sub 1 equals p sub 1, then q divided by r sub 1 is an integer and also is not an integer. So we conclude that our assumption was false, and so r sub 1 cannot be equal to p sub 1. But since the same argument works for p sub 2, p sub 3, and so on, then we conclude that r sub 1 cannot be a member of our set P, because it differs from all of its members. On the other hand, by the fundamental theorem of arithmetic, r sub 1 must be a prime number. So we conclude that r sub 1 is both prime and not prime, which is a contradiction, and therefore false. And so in case B, our original assumption that there are finitely many prime numbers must be false, as from it we have generated a false statement. So what have we actually done? Well, we started with the number q, which we formed according to this formula, and we considered the two possibilities that the fundamental theorem of arithmetic allows for q. It is either prime or the product of primes. If q is prime, then we showed that the set P containing prime numbers cannot be finite. If q is the product of primes, we similarly showed that the set P containing primes cannot be finite. And so we have shown that the set P containing primes must be infinite.